All right, I'm also going to turn off my video. I don't see any of you guys up right now, just so that I feel like that's kind of distracting when it comes to recordings. So I'm going to stop that. Okay. So today we're going to talk about, I would say in the general population, an unsung hero. Biologists love this superorganism, but most of us either think about it not at all, or we think it's a pest and we want to stomp it out and we want to kill it. Yet they're one of the most incredible organisms on the planet, and their biomass compared to humans, we think, and when the studies were done like a couple decades ago, that if you added up all of them on the planet, they would weigh as much as all the humans on the planet. Like that on its own is just mind-blowing. And they're right there, they're always there. So like, what are they? What are these things? I'm going to give you some hints. Well, first, as you'll see from this picture here, they are farmers. They grow crops, they tend their crops. They are also ranchers. They herd another organism, they keep them safe, and then that organism in return provides some nutrients for them. So already I'm thinking, ooh, life's principles. There's something on the taxonomy here. I've got symbiosis. There's already some stuff happening there. Next, they also build enormous structures, and we'll look at these a little bit today. So think about if you had a mansion connected to another mansion, connected to another mansion, and there might be thousands of these, and they're all subterranean, they're all underground. So think about it as like a really wealthy subterranean gated community. That's what they're building. Now, even more importantly, within their giant subterranean structures, they can regulate both the temperature and the humidity, like almost exactly. We can't even do that without expending a ton of energy and using crazy technology. So they've already got a one-up on us. They are also masters at building other forms of infrastructure. So they can make ladders and they can make bridges. It's pretty impressive. They can also fill holes. So if there's a pothole slowing you down, not a problem for this organism. They just fix it and continue on their way. Similarly, they can also make rafts. So this is a great example of an operating condition. We've got, oh my gosh, I forgot what I was saying. Oh, a great example of dynamic non-equilibrium operating conditions. They can leave their mansions and survive up to a week on these. All right, so they also have cemeteries and they have trash dumps, and they kind of form as the same thing. So if you are found dead in the complex, in this connected system, all the others will just walk around you and ignore you until you stink of something called oleic acid. And oleic acid, like if you ever smell something rotting, that's probably what you're smelling. So once that scent is out there, a couple of them will carry your body to the city dump and toss it all in with the rest of the garbage. So that's right, they have a specific site for body dumping, just like the mafia. Pretty impressive, love that. This picture, by the way, that is in Turkey, and I've written, I think, Cappadocia, I'm not sure exactly how to say it. If you haven't looked into that underground community, it's absolutely incredible. So just as a really cool human analogy there. I see some of you making some good guesses. Another thing, they wage really complex wars. Chemical warfare to beheading, they do it all. Now, even more screwed up. So we're not going to emulate every single thing organisms do, because nature can also be horrifying and terrible. So if you're found wounded, but you're still alive. So I don't know if any of you seen Monty Python and the Holy Grail from like decades ago. But there's like one character who says like, I'm not dead yet. That's kind of the ant here. Your sisters will come and they will slowly put you out of your misery by eating you, and then continue to battle on. Even more disturbing, they send their elderly out to die first. So pretty brutal, not something we would want to emulate necessarily. Finally, They can form multi-lane highways. They also make pretty complicated, complex gardens. To keep those things happy and healthy, they can also create antibiotics, which again, something that it takes us a lot of effort to do. And finally, they have really, tis but a flesh wound. Yeah, oh my God, I love you guys. They have so many different jobs, a really complex society. And it's a little bit like us, where when we're younger, we might have one job, and as we grow and we mature and we gain more skills, that job can shift over time. So we already mentioned farmers, ranchers, architects, construction workers, carpenters, repair people, da 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 da. They do this too. Now, a little detail I have here, and this for me was really mind-blowing. There are 15,000 species of this organism. Now, to put that in context, there are only 6,500-ish species of mammals. So that's less than half. So if you imagine all the mammals you know, and then you double it, there's still more different species of that organism. So who is doing it? A lot of you had a guess. Well, if you guessed ants, you are right. Now, there's a word called eusocial, which is eusocial, eusocial. And so bees and wasps and termites, they all have these eusocial communities. So for those of you that were like, termites, I don't know, bees, you're on the right track. One of my students last semester said, imagine the family reunion, which I thought was interesting. And they're so tiny, and they're actually already in my house. My son and I were doing experiments with them last night, which should not surprise you at all. But they can do so much, and it's just really incredible. So here's something I want you to think about for later. This isn't necessarily things you'll be writing down, but when you're thinking about your design, think about different scales. So some of the things we're going to talk about are on a systems level. So we call them superorganisms for a reason, because sometimes all of them together kind of act like one big organism. So you might look at what that whole colony is doing all together. Why are they doing it? How are they doing it? How are they communicating and collaborating together? What are the behaviors? We also might look at an individual's strategy, which could be physical or it could be a behavior. So there again, we see like a really literal emulation where like maybe you are having like, the same exact structure that you're creating, or maybe it's a behavior that you're taking sort of something from, and that's going to be a little bit more metaphorical. And again, there are some brutal bad examples of biomimicry, so we want to stay away from those. And then next class, we will get into a little bit more on the mechanisms of like that organ, cellular, molecular level sort of stuff. So you don't have to do all three of these for your design, but it opens up a lot of solution spaces. Yeah, totally. Wyatt, I'm totally with you. Okay. So their main tools, which we'll get into a little bit today, and then a bunch on the next class period, kind of fall into these three categories. And because of these three categories, they can pretty much do everything else that they can do. So these would be kind of like three big words that you might want to jot down. So we already had like, the individual, the system, and like molecular level as different scopes. And I've got dogs barking. And then these three major functions, which have nested functions within them. Navigation, how am I going to get to the place and back? Route findings, that's different. Where am I supposed to go? How can I get there efficiently? We saw that with slime molds as well. And then, as per our story, where's the stuff? Where's the stuff I need to find? How do I find the route? And then how do I get there and back and communicate those things with the rest of my brethren? Okay. So everything that they do connects there. Now, in order to understand that, we really have to look at two things. We have to know two things about ant colonies. One is their caste system. So basically, how is their community organized? Again, we're going to think about ethics here, because in human, examples of caste systems, we don't have equality, but in ants, especially if I'm thinking about jobs, all jobs are equally important in an ant community, where it's a very different in humans. So, oh my gosh, you guys. So between the hierarchy, which we have that they don't really have, and also how they make their decisions, it's a lot more equal and equitable between ants versus us. So we're going to look at those two things, the caste and how decisions are made between them. Okay, so these are things you probably have heard of before. We've got the reproductive females, which each colony has just one of the queen. We have the reproductive males, which are known as drones. And we have the non-reproductive females, which are the workers. So where else do we see this terminology? You've probably seen these before, and a lot of you said it earlier. Who else do we say? Oh, we see this in, where else? So not just ants, also bees. Termites to a certain degree too. Yeah, but bees, like we know this stuff from probably when we were kids. Now, there's a reason for that. Now, when I was in Costa Rica, like over a year ago, I was with this small group of nerds, and we had this naturalist guide who knew absolutely everything and was just amazing at pointing things out. And he said, it's no coincidence that if you look at, we were looking at bullet ants. If you look at the body of a bullet ant, and then you look at the body of a wasp or a bee, oh yeah, naked romance for sure. And they also have really interesting physiology and anti-cancer things, and can live in like hypoxia, blah, blah, blah. Yeah, you're gonna get me off topic. Anyway, they are all in the same family. They're all Hymenoptera. So the ants, for the most part, are just sort of wingless versions of bees and of wasps. So that totally makes sense when you think about their family / caste structures and their building of homes and their ability to collaborate. All this stuff should kind of make sense. Now, Hymenoptera, hymen means thin membrane, that ptera means flight. So it basically just means I've got super skinny, often transparent wings that I can fly with. That's all Hymenoptera means. And as you're familiar probably with the, oh my goodness, with the workers, computer, what are you doing? The workers, which do almost everything, are all females. So with the old Beyonce song now, who runs the world? Well, in ant colonies, it is indeed girls. So we are going to start, first of all, with the queen. So some things to note about the queen. She is huge, and you can kind of gather this from the picture. She is super, super, super massive, and because of that, she can't get around very well. So this would be like trying to put a cow in your bathroom. Yes, Wyatt, awesome. Yeah, I think it is too. Yeah, I was just reading about that the other day. Amazing. Anyway, so the queen, not agile at all. She basically stays in one place, and if she has to move, the other ants have to move her because she's kind of, just sort of stuck there having babies. Yet we know everything revolves around her, and it has to, because her only job is making sure the species stays alive. So I wrote those abs though. So one really cool thing that she has is a really extra stretchy, crazy abdomen, and it kind of telescopes out. So if you've ever like done like an outdoor party, or maybe like you've oh my God, don't stop. You have like an outdoor party, or maybe you have these in your bedroom. They're kind of like flat circle lamps, and then they go like dun, 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 and they turn into like a perfect sort of sphere lamp. That's basically what her abdomen does. So not only does it get larger in one dimension, it gets larger in both dimensions, which makes sense because those ridges have to expand, because she's going to have more and more and more eggs, and she's going to be laying those things, and she needs to be able to do that quickly because she's at even more risk when she's doing that. So like this alone, this one little mechanism alone, you could use if you're thinking about the storage of a resource and how you might use, like, oh, you've got a soft part, I've got a more difficult, harder part rather. What am I saying? I've got something that telescopes. I've got something that telescopes, outward, but it also stretches in another dimension. Like that's just one potential place where you could think about emulation. Now, what's interesting about the queen is that she's not in charge. She's not the boss. So if we think about human society, like, the queen is at the top, but again, she's just making sure that they don't die. It's just about survival. It's just about keeping the species alive. That's it. Okay, there is something, so I mentioned wings a second ago. There's something extra fabulous and demented. She is born with wings. Yeah, honeypot ants. Yes, those are amazing. Yep, look at those too. I'm not sure if I mentioned those later or not. Anyway, so the queen has wings, but once she's matured enough to mate and she's starting to form her new colony underground, her front legs reach back and she rips off her own wings. Well, she doesn't need them anymore. You don't feed what you don't need. In nature, nothing can go to waste. You have limited energy and resources, so she just rips her wings right off them. It's a waste of a resource if she keeps them. So she has to be materials efficient. Her energy has to go just to making babies. She doesn't have to move. Nobody's got time for anything else. So she rips her wings off. Now, this picture on the right, this is called a bivouac. And this thing, this is crazy to me. So these are something that army ants create. Now, army ants aren't ones that have these big subterranean places. Every day they move, they go through a new area, they spread out, they demolish all living things in their path, and they reform together. Well, since the queen can't move, what they do is they take the queen and they put the little larvae, little babies around that. And then all the other ants form kind of this giant mansion, house, cave, whatever, around the queen. So they turn their bodies, they clamp their bodies together, and they turn this into a giant moving house. Yes, they do. They absolutely do. Oh my God, I'm going to have to link a podcast to you. I think it's maybe Stuff to Blow Your Mind, but they have a 2-part series on ant warfare, and it's absolutely incredible, strange, horrible, fantastic. So here's what they do. They connect their bodies around the queen. They move slowly. And then as they go through the day and they find resources, they sort of dissolve out. They make this enormous fan. They strip all the living out of the place. And then they come back together. At night then, they'll kind of find a hiding place for the queen. They'll burrow into a log or something soft. And they'll send scouts out to go to the next spot, figure out where they're going to go. They head out real early. And then they rebuild this bivouac and they carry the queen to the next spot and they repeat it every single night. And because I'm always thinking in human terms, what would it look like if we did this? If we clamped our mouths and feet around each other and kept one person safe, like a human Pope mobile. It's this just sounds like something on a sci-fi. Awesome. Okay, so I'm gonna move on to the drones. Ooh, Ants Canada. Okay, I'm gonna have to check that out. Okay, so drones. The drones they do nothing. They're kind of if you see a stereotypical teenager in a TV show where they're just doing nothing and they don't want to help, they don't want to work, and they're just hanging out on the couch and just making garbage and whatever. That's the drones. Now, once they can fly, which is called a nuptial flight, so they've matured pretty quickly, they leave the nest. They mate as many times as they can in 1 hour. They've got usually just about 1 hour, and then they die. Now, they have to have wings because we don't want inbreeding. So they're going to go out to those other local communities. The females at this point, the breeding females, the queens, they have wings too. Then the males die. The queens burrow under the ground. They lose their wings and they start the new community. Some male ants, some drones, are known to survive about a week. But most of them die right away. Now, what's really cool to me is in that week, so as the males are kind of dying off, they've already had their little sex crazed experience. By that week, the queens are already underground, and they're already like building and building and building, with the exception of like the marauding ants, obviously. Now, E.O. Wilson, who any of you that are like ant nerds like me, you probably are already familiar with E.O. Wilson. He's like the world's premier expert on ants. And he once referred to reproductive males as flying sperm missiles. Short-lived and they get the job done. And I just think that's like a hilarious analogy. Okay, so that's drones. They just sit around eating and making a mess, have sex a lot, and then they die. Maybe it's a good life, I don't know. Okay, so finally, and this is like almost all the ants in the colony are the non-reproductive females, which we refer to as the workers. So as I alluded to earlier, who runs the world? Girls. In an ant colony or in a termite colony, that would be true. Now, the workers that are all females, you'll notice that they have different morphological traits depending on what they were born to do and depending on what happens to their genes. And when I say morphological traits, I mean like physical structures. So usually internal morphological traits we would call anatomy. Morphological traits, we usually consider that like more the external surface, and then like physiology would be like more like the chemical processes and like how it does the things that it does. So if we look at the external morphological traits, and then we look at the anatomy, we see there's a lot of differences. So first, the workers don't have fallopian tubes. So even if they like created an egg, they would have nowhere to send it. So like already we see a difference in anatomy. Second, their ovaries are super, 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 super tiny. So like they couldn't have babies if they wanted to. If they made some sort of egg, they couldn't send it anywhere. So like instead, just like bees, they do literally everything else. So I mentioned that they're called eusocial insects because they have really complicated societies. They vote even. And if you've seen, there's a guy who wrote something called The Honeybee Democracy, and he talks a lot about like how they vote and they make decisions together. It's really amazing. And different body forms that they have are going to do different jobs. So some of them, like this little minima one here, might tend the queen and the babies. You're probably smaller and you're probably younger because your queen's going to be buried sort of somewhere deep inside, and you need to be able to get around her because she's so huge. So you might be like one of the little tiny ones. If you are going to war, if you're going to rip the head off of something or you're going to eat one of your brethren, you are probably going to have way bigger mandibles. You're probably going to have way bigger heads. And a lot of these ants also create something called formic acid, which is where like the chemical warfare part comes in. So they can not only like crack the heads off of other organisms, but also they sometimes will go with workers who are on like a food finding mission. And like if they find a seed or something, they can use their mandibles and their heads to like crack or bash open seeds. So sometimes it's kind of like the bodyguard who can do an additional function to help those out. They also can, and so that worker, just sort of the general worker, those are often the food collectors as well. So a few details on that, and I mentioned some of those things here. So I mentioned in the very beginning that ants are both farmers and they are ranchers. And I'm sure you're familiar with this first part with the farming. So we see that in leafcutter ants, oh my God, computer. In leafcutter ants, we see that they'll, use their little mandibles, they cut off a piece of leaf, they carry it over, and they put it in one of their tunnels, which they have to have the temperature and the humidity just right, or this won't work. The leaves don't feed the ants. The leaves feed a specific fungus that they are farming, and then the ants eat the fungus. This is also where the antibacterial properties can come in. So the ants have to constantly tend to make sure like other fungi isn't growing, that their fungus is really safe. So the leaves feed the fungus is then farmed, and then that in turn feeds the ants. Like just something like just a crazy example of this. I think maybe I have this on the next slide, and I'll come back to the ranching in a second. So to get a sense of how big these things are, I'm going to go to the ants and the aphids in just a second. So They can carry up to 50 times their body weight. So I'm 5'4", I'm about 130 pounds. So imagine if I took a grand piano, put a grizzly bear on top of it, had him holding a punching bag, put a giraffe on there, and then I went and got as many groceries as I could carry, and that was like all in one big pile. That's like the equivalent of what a leaf cutter ant can do. Like, what? That's insane. Now, obviously, so there's some scalability problems with emulating something like this. We see when we talked about bioluminescence, how like organisms way back then with higher oxygen, better respiration. We see differences in like, hot-blooded versus quote unquote cold-blooded organisms, exoskeleton versus endoskeleton. Like, we know that there's some limitations around emulation here, that we can't always create what the ants are doing. But again, if we think about emulation on a small scale, and we have a whole ton of creatures all doing something amazing, then maybe there's more potential if we think about a system. Now, some of you are already, yes, I'm totally with you, Wyatt. Some of you already know about the aphids. And so those teeny little green guys on there, not guys, actually, they're mostly female, are aphids. Something crazy about aphids, just as an aside. Aphids are born pregnant. So like, imagine if you're female and you were born, you're like already pregnant as like you come out of your mother's birth canal. Like, there's just some like completely insane biology there, and like different generations kind of do different things. So like, you should look into that because it's wild. Okay, so the aphids have like little like stabby mouth parts, and they'll go usually to a stem and they stick their little stabby mouth part in there, and they suck up all the fluids from inside of particular plants. Now, just like bees, will get the nectar and they like concentrate it by like barfing back and forth into like other bees' mouths, and they concentrate it. Instead of doing that, the aphids like concentrate it through their bodies, and then they poop out like candy, basically. So they little candy poops. So then the ants are like, hell yeah. And so then they follow the aphids around and they like eat their little candy poops. So they're ranchers though, because they take care of this herd of aphids. And so like they can kind of herd them together. They make sure they're safe. If they sense another predator, they will protect the aphids. If there's a plant that is like starting to, yeah, no kidding, Grace, like they're hard to get rid of. Because again, like they're born pregnant, they can like breed like crazy, just madness. Anyway, so the ants, if they see a predator, they will attack. If they see, ooh, this plant might not have so much fluids inside it anymore, they will pick up the aphids and they'll bring them to another plant. If it's raining really hard, they will pick them up and they will sort of corral them underneath a big leaf. So like they really take care of their herd so they can get that high caloric butt candy. Cool, fun times. All right, so moving on from there, we mentioned a little bit earlier on in terms of architecture and engineering and construction. So I'm thinking about all these worker ants and other things that they do. If this is, again, these are the subterranean ants. This is not the army ants this time. So if they have an example of dynamic non-equilibrium, which is going to be, it's like a massive storm flooding tons of water, they will form a raft. So they all will escape their underground home. And then they have some hydrophobic properties in their body. So just like think about like a wax or something oily on the outside of their body. So individually they can float. And so they'll create this kind of like pancake raft sort of deal. And the reason that like how they do this is they find the edge. So as they're kind of like all going up together, I like keep gesturing and it doesn't matter because you guys can't see me. So they'll spread out until they find the edge of the raft, and then they hook at 90-degree angles to the last ant. So their jaws will clamp on one, their legs will clamp at another, and then they have all these different little 90-degree patterns. More ants come, they go to the outer edges, and then all together they can float, which is pretty incredible. Like they can sometimes last up to a week floating like that, especially as long as like we've got like, maybe not like super insane like hurricane strength winds. And then as soon as they're back on mostly dry land, they just rebuild their colony, which is pretty amazing. Yeah, I'm sure some probably could drown, but again, because of their hydrophobic properties, as long as it's relatively still water, like flooding is probably better than like a huge, huge, huge storm that's like pelting down on them. And they reach land within like a few days, they're for the most part not going to drown, but they can. All right, so another example is that they can make bridges. And so what's really cool about this, so they do the same exact thing. They find the edge, they climb to the edge, and then they reach across and they hook to each other. So it's like mouth, leg, mouth, leg, mouth, leg. They all connect. And then all the other ants can go across. Now, what's interesting about this is that somehow, and I'm guessing it's chemical signaling and pheromones and stuff, just like the slime molds, they know how many ants are behind them. So they can make the bridge really wide. And then as they know there are less ants, they can make it skinnier and skinnier and skinnier and skinnier until they don't need all those lanes of traffic. And then they sort of close up and they move on, which is really cool. They can also make ladders. A ladder is just a vertical bridge, really. So if you're thinking about how are they going to move, well, they're going to make ladders and bridges out of their bodies. This is also where that pothole idea comes to play. So as they're, scrounging around and they're looking for food, again, this is going to be, a lot of army ants doing this since they're the ones that are out and about more likely. If there's a big divot in the ground, they want to move more quickly over it. Some of the ants will lay down in that pothole and all the others can go across super fast. They're really efficient. Okay, so again, worker ants, what else are they doing? So they're making ladders, they're making bridges, they're ranching, they're farming, they're taking care of the young. They are bringing dead bodies and garbage to the garbage dump. They are keeping it clean. They're like all of these things. They're going to war. They're beheading their enemies. We also know that obviously they are making, some of them, absolutely massive, ridiculous, huge homes. So just like your average boring normal ant probably lives in a colony of tunnels that go like 7 feet deep. That's just like the basic standard model. 7 feet, no upgrades, 7 feet. That's crazy. Now, one of the biggest finds that we found was in Japan, and it was about a square mile large and up around to like, 2000, year 2000. Most scientists thought that it was the largest ant colony in the whole world. It was just like this super colony. In Japan, again, they think it has like somewhere between like 40 to 40,000 different nests that all connected together. So again, this idea of like a huge gated community is kind of like that. So they have all these tunnels connecting all these like super colonies and like 650 acres plus. They think that in that super colony, there were over 1 million queens. So if each queen has a community and then those are tunnels are built out to the next and the next and the next, like 1 million queens, that's crazy. And over 300 million worker ants probably living there. They also think that that colony that built that so big was maybe up to 1,000 years old by the time that we came and destroyed it, because of course we did. We needed, more parking lots and more shopping centers and more whatever. So this massive colony doesn't exist anymore, but at least we have some of the cool data. Now, the newest large one is the picture that you see here. So this is an abandoned leafcutter ant city. This is in Brazil. They also believe that this once housed millions of ants. This one, humans didn't drive out. It was found empty. So I think about like places like Mesa Verde and other abandoned civilizations. This is kind of what this is like. So super huge. They had a ton of like super highways and gardens. We're not really sure why they evacuated, but like everything is in kind of pristine condition. And what's really cool, and there's you can see these things a little bit here. Okay, so they wanted to, as they were digging, they didn't want all these tunnels and stuff to be destroyed because like there's so much to study there. Like, what if we wanted to build subterranean structures? There's all those, oh my God, I forget the names of the people who like are like the preppers for the apocalypse. Like if we're gonna build a subterranean structure, how could we maybe do it like ants do since they're so just amazing at it? So what they did, you can probably tell this, is they poured concrete in there, and then they're basically preserving the city. So as they dig around it, they're not destroying it. So this particular one in Brazil didn't stretch 7 feet below. It stretched 26 feet below the surface, and it took up like 500 square feet of space. Like, that's incredible. But okay, again, not all ants are subterranean. Some ants, okay, and I just have, those are some of the facts. So there's like the Japan and how big it was. Da, da, da. Okay, now some ants also live in trees. In like Costa Rica and stuff, you'll also find like termite and ant mounds like high in the trees that, you know, have more of that sort of soil thing. Yeah, that's what we'll have to do on Mars, seriously. Okay, and then we also have, yes, we have these weaver ants. This is the green tree ant. And they form nests by stitching leaves together. And how they do it, amazing. Okay, so they pull everything together, they find the edge again, they pull it together, and then they take their babies, they take their larvae, and the larvae, just like how spiders make silk, their larvae make silk. And so they use the butts of their babies to glue the leaves together. Like, can you imagine like having your child and like using something that comes out of its butt to like glue your house together? That's insane. I love biology. Like, you can't even make this stuff up. Yeah, amazing. So like, here's another example. So all of that like webbing that you see here comes from a larva. You see it holding it in its mandibles, and they're just like squeezing it like a little glue bottle. Amazing. Until you have something like that. Okay, and obviously I mentioned before those bivouac things where you've got the ants that form, you know, the structure around the queen and they move. Just a couple of little details around that. When you have one of those bivouacs, which is, and that is, that's this thing right here. They think, as the army ants are moving, that there could be as many as like 700,000 worker bodies that are around that queen and linking their legs, et cetera, and there also might be thousands of larvae that are in the center with that queen. And again, if I'm thinking about those females that are doing all of this stuff, you know, you're going to also have little specialized ones. They're like feeding the queen and taking care of all the babies and like all of that stuff. All right, so again, crazy specialized. In some of them, they might be born with a specific body plan and they don't change it too much. Other ants, and like, again, like we looked at this kind of back, where are you? Other ants might start off their life looking like one thing, and then as they age and, you know, hormones and pheromones change, they can flip different genes on and off, which will then create different phenotypes or like things that we see. And so some of these ants, like their body plans change as they get older, which is really interesting. Not all of them, but some of them. Just another cool little fact. Oh, I'll have to look into that book series. Oh my God, if they squeeze harder. I imagine, like, you know, they don't want to kill their babies. So imagine how many babies that they have to have on hand, because you probably can't get that much silk from one. So like, I imagine like glue bottle, you know, kind of like a surgeon being like, you know, clamps, and then they like someone hands them another baby and they butt glue it and then they give them the next one. Oh, the lifespan of females, that's a really good question. I honestly couldn't tell you. That would be something that, oh, a month or two. Gotcha. So that's pretty long. Yeah, a conveyor line of babies. That's like exactly what I'm thinking. Awesome. I'm glad you guys know these details. I'm terrible at remembering numbers. Okay, so just one quick fact I wrote on here, because again, terrible at numbers. If we think there's 1.4 million of them, that is for each one of us. So there are not quite 8 billion of us. So if there's 1.4 million for you and for me and for the next guy, like that's why I was saying, like, that biomass component, if you add up all their bodies and how big that is, you know, like, you know, this data was taken like a few years ago and we hadn't reached this many billions of people. But at one point, not that long ago, like a decade ago, like they had the same amount of mass on the planet as we did. We just don't see them. Like, amazing. Okay, now this is just like another little fun fact here. There are also these crazy ants with these heads that when they are in the ground and they're trying to like block other ants from getting in and waging warfare, they've got these big flat disc heads. So like that's like a door. So they shove their heads in there and they block anything that's like coming. So again, like the morphology and the different types of workers, like it's just like, it's amazing. Okay, now, computer. Okay, so this is the thing that makes me so happy about all these workers versus the queen and whatever, is that no one's in charge. The queen's definitely not in charge. And like we always think about, the queen is ruling and she's telling everybody else what to do. No, like that is not what's happening here. Nobody tells somebody else what to do. So how is it that they can form these really complex societies where they can collaborate and coordinate and manage disturbances and self-organize and find and distribute resources? Again, taxonomy, 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 taxonomy. How do they do all of that? Oh my God, is that you, Hodor? Yes, yes, it is. How do they do that without a leader? Okay, so the best way to think about this, oh my God, I love you guys so much, is you kind of have to compare what we do as a society to what they do as a society, and then it's a little bit easier to explain. Okay, so humans have, and this is, I'm getting into the life's principle under adapt to changing conditions a little bit, and also integrate development with growth. So there's a piece of embody resilience through variation, redundancy, and decentralization. And then also self-organize and build from the bottom up. Those are kind of three things I'm looking at there. So if you think about humans and how we organize complex businesses, societies, whatever, we have one command center, and then all the information flows from that boss or a small group of people that tell everybody else what to do. And then there's more people that take, those directions, who give it to the next group of people, down, 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 which means at the top, that power is hoarded, that knowledge is hoarded by one group of people along with our resources. We know that. And that information just kind of trickles down. So when we talk about the caste system, like we know that some jobs are quote unquote more important than others in corporate pyramids, like you see all of this. Now, the problem with this, think about this as like a game of telephone, where we often see like the person at the top will like give directions, and by the time it's like to the bottom people, like things get screwed up. And similarly, if there's like, the people who are starting off at the bottom, they might know something really important and need to make a change, but then they have to like tell it to their boss, who tells it to their boss, who tells it to their boss. And so the ability to make quick change is really hard. So our organizations aren't super resilient because you don't have direct lines of communication. It's like follow the chain. And then like things like the purpose and the rationale and the buy-in and like the ethics and stuff, like all of that, could start at the CEO, but it doesn't mean that it's necessarily true for like the employees. So like Jeff Bezos, Amazon guy, might say, oh, blah, 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 I respect all the people's rights, and et cetera, et cetera. And then like you go down to the actual employees in the factories, and like some of them are wearing diapers because they can't pee because they have to like scan a certain number of things in the hour. Like gross, right? Now here's the other problem. Not only do we have slow communication, screwed up communication, ethics violations, et cetera, and et cetera, but what happens if the boss dies? If I've got some people at the top and now they're suddenly gone, now some of those skills are gone and some of that knowledge is gone, and now we got to wait and train a new one. Again, we've got this really slow turnaround. So again, information's going top down. That means we probably are focusing more on competition rather than collaboration, because everybody's trying to like get to the top. So like that then dictates a lot of what our society is. So again, we don't have a lot of feedback loops here. Information's going top down. We've got kind of classes or caste systems, even if they're like unofficial, and being cutthroat is like incentivized. Like It doesn't matter about the next person. You knock your stuff out, you try to be somebody else's boss. Now, if you are an ant, you do the exact opposite thing. There is no command center, there is no boss in the ant world. So ants, again, if I'm looking at integrating development with growth as a life's principle, ants build from the bottom up. So not only is this true like in their rafts and their bridges and like literally they're building from the bottom up, but behaviorally, so on a more metaphorical level, they are making tons of tiny little relevant interactions from the individual to the person right next to them. And then through these like tiny little simple rules, and by following those simple rules, they create these really intricate systems and structures and feedback loops that are like immediate and super fast because they're just hyper localized and they're paying attention to like exactly what's just near them. And you might have heard this word before. We call this property emergence, where you have something simple and then just a couple little simple rules, like if you do this, I'm going to do this, and that cascades through the colony super fast until we see a big change. So think of this like, here's an analogy for you. Think about like fractals, where you've got like simple rules of math underpinning everything. So like, if you go to like a small shape and then like you build up and you build up and you build up, you see like the coastlines and clouds and all this stuff, like they form the same shapes, but it's just like a simple mathematical rule that they're following. So I've got super fast information that's spreading, which means I've got a super fast reaction to that new information. It's being passed in all directions. So just like, if you're at a stadium and like everybody does the wave, but now you're going in all directions, that information is happening while the other ants are experiencing it themselves all at one time. So that means I've got tons of feedback loops all the time. Any change in the environment. So if I've got an operating condition, which changes, maybe I've got, more humidity, I've got rain, I've got a fire. If I've got, other ants that are trying to attack, it could be biotic, abiotic, whatever. Any change in the environment, in ant health, in architecture, predation, food source, whatever, they spread that message out and they can act right now. So all the ants are important. All the ants are reacting and sending out messages based on their own experience, which means nobody is more important than the other. They're feeding all their information into the whole. So what's great about this is that, like, again, if something happens, the whole system doesn't collapse the way that it can with us. We don't have like a 1%. We don't have like different ants worrying about like resource acquisition or anything like that. Like there's a lot more equity and equality here because everybody has a say and they're acting immediately to the environment they're in now. So we also see this just as another example in like murmurations. So like if you've ever seen those videos, I'm gesturing again, or like the birds, like there's a ton of birds and they're all kind of moving in these like beautiful, crazy shapes, like all together, or like schooling fish, that like synchronized, beautiful movement. That's the same thing. They're following really simple rules. If you go this way, I'm going this way. If you go this way, I'm going this way. And, depending on how far apart they are and whatever, they create this emergence property. So yeah, the sum is greater than the parts for sure. And we also saw this sort of feedback loop idea in slime molds last time we met. So again, this will be related to like a tiny little assignment that you'll have for Sunday, is looking at some of these positive and negative feedback loops. So just as a reminder, positive feedback loop is really like, it's not a positive, it's not a good thing, it's additive. So, as something happens, more of that same thing happens. So with the slime molds, like, a bunch of them grouped together to form that slug, and as more groups together, even more grouped together, so that causes even more groups together. So an action creates more of the same action. That's a positive feedback loop. So it's out of whack. It's like there's some sort of disturbance. The negative feedback loop, it's not actually negative, but if you think of like a plus sign and a negative sign, it's balancing. We're maintaining equilibrium. So we saw this also with the slime molds, where they were like, okay, I'm finding food. I'm going to do a positive feedback loop. Hey, there's more food, more food, more food. Let's all go here. Let's all go here. Let's all go here. And then when that food source dries up, then they go pull back, pull back, pull back, and then they create sort of homeostasis again and let everybody know. I guess that's kind of a positive feedback loop too, because they're like now doing the opposite, changing and shifting. Like, I guess it's really like if they're going down a new path and they're just like searching for the food and they're like, nope, there's none down here. So let's all head back. And we're going to like make a little chemical marker here to say nobody else go down there. That's really more like the negative. So both ants and slime molds are kind of doing the same thing. All right. So I took some notes for you. Oh, let me just give you like a couple more examples real quick, actually. So humans do this sometimes. So think about traffic. We're getting our cues both from around us using our own experiences. So like we're looking at what the other cars are doing. We don't have chemical signals most of the time, but we've got like changing lights and we're looking at the speed of different cars. We can get warnings from other people if they're like honking their horn, so we can change our immediate surroundings like in the moment, detour signs, or like, even if like we're out and about, like if we smell something delicious and we see like a donut shop and then there's a huge line, you're like, well, do I make the choice to like join these people, or like is it not gonna, that resource acquisition, maybe that's not as important. So like we also use multiple senses to detect like what other people are doing and changing our behavior. We just don't do it in terms of like business and job. It's more just like, when a group of us are together. Okay. All right. So how do they do this? So I jot down a few little notes for you, and I think I have pictures of these, so I can send these to you later. So again, this idea of feedback loops and constant communication, and sending a scout out to figure out where stuff is, all of that's done through pheromone tagging. Pheromone is just a nice, smelly little chemical that can either say definitely go there or definitely don't go there. So the ants will leave their nest and they have no idea where that resource is. And so they're all traveling at about the same speed. And every little bit they go, all right, I'm going to like scent marker, scent marker, scent marker, and I'm going to leave a tiny little pheromone there. Now, this one had to get really far away to get to this resource. And so by the time this ant gets way out here, these pheromones have like dissipated into the air already. So like think about if you've ever gone into like a mall and like some old lady tries to like spray you with perfume. I don't know that they do that anymore, but like as you get away from that perfume counter farther and farther and farther, you don't smell that thing anymore. Or like the same thing of like off gassing and like a Target. If you go into that like laundry detergent aisle, it's like really strong. And the farther you get away, you can't smell it anymore. So because you can't smell it anymore, the other ants kind of know, oh, well, like I'm not going to go down that trail anymore because it's clearly not very strong. On the flip side, if an ant's doing the same exact thing, leaving down a chemical trail, they get to something much closer. Now they double back and they leave that pheromone again. So now this trail becomes strong as this trail is becoming weak. And so I see a positive feedback loop here where then another ant comes and it goes to the resource, and then it goes back, leaves another trail, it goes leaves another trail. And then once that thing is all done, then they might move on to the next one. So again, they don't know where the farthest one is, but through that chemical tagging, they can sense the concentration and they know where to go. So who got back the fastest? How do they get their way back? We'll look at that in just a second. And how do they tell? Well, they leave those chemical markers. Okay, so we kind of looked at this. So again, like Hansel and Gretel, like the little breadcrumb idea that's happening there. Now, what if the trail really sucks? Because we see this in like the slime molds. You reach out, you're using your resources and you're pulsing and whatever. What if like you want to tell everybody don't go down there without like going too far away? Well, if you're a pharaoh ant, you don't even necessarily go all the way to a resource. You kind of like just like you go out a certain distance and then you go, no, it's not even worth my time anymore. You come back, and instead of using a chemical tag that says, oh, there's something way out there and waiting for it to dissipate, they put a little stop sign tag there. So they just go like, don't enter here. This is a waste of time. Like, don't even bother in this place. Other ants, so we talked about this with the bivouac idea. So this is a little different. So these are the pharaoh ants, and then these ants right here. I'm talking about if I have a more permanent nest, I'm going out, I'm finding a resource, I'm bringing it back, I'm changing the trails I'm going on, da 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 da. Same thing with the pharaoh ants. But what if my home base moves? And what if I'm trying to travel in huge numbers and not just kind of like one ant at a time? Well, so army ants, which these in particular are found in Panama, they do something a little different. So we have our little bivouac thing. I've got all the workers around here, and then I've got the queen and the larva in here. So they move. Once they get to like a good area, that thing fans out so they can cover as much space as possible. But here's what they do. They create like a multi-lane highway. And I kind of mentioned this in the very beginning, where the people that are going out, ants, they fan out more drastically because again, they want to like reach as many resources as possible. So they kind of go to like an outer edge. They go here and they go here to like the sort of the outside edges. And then once they start finding things, then they bend their way in and they start carrying that stuff back down to the middle. And this is really cool because now they can not only smell and sense the food, but they can smell and sense each other, and they're blind. They're blind when they do this. So they're completely using like, pheromones and like the smell of the food to like, one is like kind of like touching the butt of the next one. And so like they're all going in this line back to the, the bivouac or whatever, and like allocating those resources as they need to. So they go out, grab the thing, go back in, and again, their blindness, they don't need to see because they just start looking those those pheromone trails. What makes them blind? They just don't. I mean, they probably have eyes, but they don't like that stuff's just not connected, so to speak. They've evolved away from it because their ability to find and react to pheromone trails is just so much stronger. That's how they evolved. Yeah, and again, they don't get lost because they can smell around them. Okay, so that's, I'm moving away versus I'm sort of staying in place and they're not getting lost and whatever because they can smell what's happening around them. And we'll talk next class a little bit more about that chemical tagging and like the mechanism that goes there. Okay, now, so I said, okay, they've got chemical tagging. They can go out and they can figure out what are the best routes, the most efficient routes, where's the food, where's the stuff. Then they can, when they come back into their nests, they also have behaviors within the nest where they will allow the ants that take care of the queen and the babies, like they move more to like the top. And then like the ants that come back with the resources will like feed them first, and then they go back to the queen and the larvae. So like they, there's some like priorities there in terms of like, keeping the species going. But what if something happens and they get really far away, and maybe that's their only resource, and like maybe they're lost now and they can't get home and their like chemical trail is gone, or it like, goes away, whatever. Well, they have multiple different ways of getting back home. So some ants have what we call allocentric navigation. And all that really means is they can tell where the sun is in relation to where their nest is. So this is a great example of the life's principle incorporating diversity, because you've got a bunch of different ways to figure out how do I get back home if I'm not just following a chemical trail. So they're basically using the sun as a compass. And they look at the sun's, like the angle of the sun, kind of like how we might use like a mirror to navigate. And we're like looking at an angle. That's like what they're doing. And then they can use that to go, okay, I need to go this way. Bees do this. I just wrote that on there. Bees do this with their like little waggle dance that they do. And so like for them, they point in a specific direction. And obviously that tells like the bees go this way, but then the longer time period that they're dancing is like a longer distance away they have to journey. And this is what gets into their voting system, is like just because of those feedback loops and how they're all immediately getting information from everyone around them, they can quickly figure out who has the shortest route and what direction it's in from the movements of this dance. And then they can all find, that meadow where there's nectar, or perhaps a new place. Now, what if, so going back to ants, what if I don't have a chemical path anymore? And what if there's no sun? Well, they can also use terrestrial clues. So they can remember like the frame of reference. So it's like, oh, okay, I saw that log over here, and I saw this and I saw this and I noticed this. So they can use landmarks, some of them, which we do. So visually, those that aren't blind, they can do this. Others can basically memorize a path, and they have a built-in odometer. So they can kind of like count their steps and like remember exactly how far they went and what that path was. That's not dictated by a chemical tag, but is like an internal mechanism that the ants have, which is pretty cool. Now, again, if the sun is unavailable, I skipped this part for a second, they do something crazy. So when the ants, they're forming their nest and they're new ants, what they will do is they'll come out of the nest, they'll turn in a circle, they'll go back in the nest, and they'll come out of the nest and they'll turn in a different circle the other way, then they'll turn this circle the other way, and then this circle the other way. Yes, I think wasps do use some visual markers that are on the ground. I see those actually in my yard all the time. The like wasps going down in there. I should pay more attention. So as these ants are turning and turning and spiraling around their little nest, what are they doing? Well, they're actually using like magnetic fields to figure out the direction that their home is in as well. And so I'm pretty sure there were some scientists that like picked up a bunch of these ants and like put them into, this might be my next one. What you doing there? Notes. Okay, I guess I don't have a picture. So they put these like little magnetic coils around them to like screw with the ants, and the ants did the same thing. They came out, and they reoriented themselves to where the new magnetic fields were. So it's like they watched them in situ in their habitat, and then they moved them, changed the magnetic field, and they could find their way back to like the new nest spot, but they could not find their way back to the old nest spot because their orientation was all wrong. So like this idea of like biomimicry really needing like scientific discovery and the scientific method, like without that, we can't learn from these strategies and use those strategies. Now there's one last little one. Oh, here it is. That's what I was saying. So they put these like giant coils around them and then like messed with their brains. Okay, so then I talked about this a little bit already. They can use those sort of visual cues and say, oh, I remember that, I remember that, I remember that. And I kind of have a sense of like the direction, and I know how many steps I took. And so they can find their way back. So again, if I'm thinking about not only resource acquisition, but then getting those resources back somewhere. So I've got, the paths to go. I also have the paths to come back. I might have another path to bring that resource to somebody else. So like all of this stuff is super relevant to our task. Now, there's also another form of ant. Now, this happens in the desert where resources might be really, really far away. And so like the big ant might like carry a little ant on its back, and they'll go do. And then like once they're at a specific area, and this little one is blind too, they can kind of collect materials together and then find their way back, which is cool. So we've got some piggyback rides happening. And then we also know that some ants, especially this is in like if the operating conditions are like a really tight space. So like if it's a desert, really, really big spaces. This is the flip side of that. So if different operating conditions, hint, hint, they can move backwards. So they'll go out, they'll get the food, they have a visual memory of that route. They'll start walking backwards. If they can, they'll turn around, then they'll flip back to going backwards, because sometimes that food particle is just too big for them to turn all the way around. So they might just be able to turn like 180. They can see what's happening behind them. They go back and they walk backwards all the way to their nest. So I've got sort of two different scenarios here. So again, if I'm thinking about resource acquisition and getting that, I have different strategies that I might be using based on what's happening in that environment. Yeah, so really cool stuff. Okay, so that, oh, thank God I finished like basically right on time. So that is all the crazy stuff I have about superorganisms and ants today. Again, what I want you to do after you have finished up your notes, I can share this presentation as well. I'll put that up for you guys soon, is go through it again, use your taxonomy, what I did on mine. Stop sharing for a second so I can show you. So again, what I did on mine is I went through the taxonomy, and I just went through and I circled both the large category and the smaller categories that everything fit in. Oh, one quick note before we go. I want you to look at process information. A lot of times people screw this up. Sending signals, processing signals, and receiving signals are three different things. And if you look at the sensing versus the sending, you'll see some of those same things. So a ant might be sending out a chemical signal to go somewhere, but then on the way back, it might be sensing like the sun, or it might be sensing like, you know, something else in the environment that's visual. So it's not always going to be the same thing that they're putting out as the thing that they're using to navigate back. So just be really careful on those. So again, I, you know, jotted down some big ideas. I circled all the ones that were the most relevant. That's going to help me with my challenge. And then after that, I also got my life's principles, and I went through my notes and I jotted down, like these I'm not going to share with you. I jotted down where the little examples are with all of these things. So take pictures of notes, take pictures of these things, post those things by the end of tomorrow. Then you'll have a tiny feedback loops assignment for Sunday. That's all you'll have. And then on Monday, we will get into the smaller scale stuff. So today we talked about large sort of system, whole colony, and a little bit about individual behaviors and like the queen's abdomen and some of those things. And then the Monday we'll go small and look at how they're actually sensing some of these pheromone trails and such, and going on like a much smaller scale. So again, in terms of thinking about your designs, all those different scales are going to lend themselves to different solution spaces, which should be good for you. All right, so that is everything from me today. I hope that was interesting for you, and I will post an announcement and probably shoot out an email when your little tiny assignment is up. All right, before we go, any last questions for me?
I wanted to ask about the design project. Like, we haven't been given any. Okay. I just wanted to make sure I didn't miss it.
Nope, you didn't miss anything. It's going to be really similar to what you guys did with bioluminescence, just with that change in operating conditions. So now I'm not thinking about like electricity and lights anymore. I'm thinking about something a little bit different. So we will revisit that next week. And then I'll give you kind of the framework, but it's basically the same thing, same process as you did with bioluminescence. So very good question. I have not given that to you yet, so don't worry about that yet. As long as you can connect the slime molds and these ants, and we'll do one other organism, superorganism next week, to the life's principles and to the taxonomy, you'll be in really good shape.
Okay.
Thank you.